In this problem, the first thing we're being asked is to find w prime of 12. We don't have an equation for w, so we can't find the derivative. Therefore, our best shot is to look at the table. This table matches w. And 12 is right in the middle of 9 and 15. So if we can find the slope between those 2 points, we'll have our best approximation of w prime 12. So our first point was 961.8. Our second point was 15, 67.9. If we want to find that approximation for w prime of 12, we just calculate the slope. 67.9 minus 61.8 divided by 15 minus 9, and we end up with 1.017. It's also asking us to show the computations. We did that. Using correct units, interpret the meaning of your answer within the context of this problem. What really helps us answer that is looking at the units that we're dealing with. We've got degrees Fahrenheit on top. We've got minutes on the bottom. This is really a rate of change in degrees per minute. So we should say something like the water temperature is increasing at a rate of approximately 1.017 degrees Fahrenheit per minute at time t equals 12. Including that piece about at t equals 12 really shows that you understand that this is just our approximation for t equals 12. That rate of change might be very different at different times. That's it for part A. Part B asks us to use the data in the table to evaluate the integral from 0 to 20 of the rate of change of temperature. We also have to interpret the meaning of that in the context of this problem. The fundamental theorem of calculus tells us that this integral is equal to w of 20 minus w of 0. We have those numbers right there in the table. We know w of 20 is 71. We know w of 0 is 55. Subtract that, we get 16. We're also asked to interpret those units. It helps us to understand that these are units in degrees Fahrenheit. That might give us a clue. And because this w prime t is the rate of change of temperature, antiderivative would be the change in temperature. So you should write something about how the temperature changed by 16 degrees during those 20 minutes. And that's it for part B. Part C tells us that from 0 to 20, the average temperature is given by this integral, which is pretty friendly for them to tell us because we should already know that. It's telling us to use a left Riemann sum with 4 subintervals to approximate that integral. We have to use rectangles because we don't have an equation for this function. So let's go ahead and do that part right now. We need to find area using left-hand rectangles. Looking up at our table, looks like the width of our first rectangle is going to be 4 multiplied by the left-hand value, 55, at which point you keep going until you get all 4 rectangles. We can see the next rectangle is going to be a width of 5 using the 57.1 and so on. After pulling this data from the table, we can use a calculator to put all that in, see what we get. Turns out we get 1215.8. So that gives us our approximation of the area using left-hand rectangles. We have to multiply that by 1 over 20 to get the average value. Which turns out to be 60.79. That's the average value of the function from 0 to 20. And we can look at the values of the temperature to see if that seems reasonable. About 60 seems good. Our range goes from 55 all the way to 71. The tricky part of C is this going to be an underestimation or an overestimation? And because this whole function is strictly increasing, let's think about what that means in terms of left rectangles. We have some strictly increasing function, and we make rectangles on the left. We can see pretty easily that those are going to be under approximations. So we should write something about that. The approximation is an underestimation because exactly what we see. A left Riemann sum is used, and the function w is strictly increasing. Total points for this problem were 3. You got a point for the correct left Riemann sum. You got a point for your approximation. And you get a point for your underestimate with reason. I apologize, I forgot to say where the points came from on part A and part B. On part A, the points were 2. One came from your estimation. That was the 1.017. And 1 point came from your interpretation with units. Part B, you got 1 point for the value, 16. And 1 point for the interpretation with units. So you had to have that degrees Fahrenheit and explaining what that 16 degrees really meant. That's it for part C. Part D tells us an equation that works for W prime starting at 20, which goes beyond our table. It's asking us what the temperature is at time t equals 25. Well, that would be whatever the temperature was at 20, plus the change in temperature starting at 20, going to 25, of W prime t. But we know what W prime t is on that interval. And we also know what W of 20 is. From the table, we know W of 20 is 71. We know the equation for W prime t is 0.4 cosine of 0.06 t. That was given to us in part D. You could go ahead and figure out that antiderivative by hand, but why would you when this is a calculator problem? Just put that in the calculator, and we end up with 71 plus 2.043. And you don't even have to add those together, but you could. 73.043. And our units are degrees Fahrenheit. Part D was worth 2 points. The first point was for your integral. Had to see that somewhere, or this would be fine. Your second point came from your final answer. That's it for part D. And with that, we are done with 2012.